Hi everyone, so welcome to this video on closed form solution of linear regression. And in linear regression we studied about one algorithm, gradient descent, which helps us to minimize the squared error loss, right? But in this video I'm going to show you there is another method which is called this closed form solution, which will help you to find out the right set of theta by just using this formula, right? So this is called your closed form solution of regression, and we will first prove this formula in this video, and in the next video I will show you the implementation in Python. So let's get started. Yeah, so let us first talk about regression, right? So regression is a problem in which you are given some data and you want to find one line which is a best fit to this data, right? So there can be multiple lines with different parameters theta. So when I talk about theta, so consider theta as a vector of theta naught and theta 1, right? In this case, right? And if you have data set with multiple features, then you will have more values of theta, right? So let us think of this data set as a matrix. This matrix is also called as a design matrix, right? So X is a matrix which contains m training points, and each training point has n number of features, right? So m represents the number of examples and n represents the number of features, right? So the ith entry, right? So this entry represents the ith example, this ith row, and particularly if you talk about some coordinate, so if you talk about x, I, j, right? So this basically means ith example and the jth feature, right? Okay, so what I'm going to do, I'm going to denote entire row as the first example, this is the second example, right? This entire row, right? And similarly the last row is going to be my mth example, right? So we have data which is arranged in this form. This is called a design matrix, and the goal is to find right set of parameters theta, right? So theta would have n cross 1 dimension, right? So theta would be, if you have n number of features, then you will have n plus 1 parameters, right? So in this example you have only one feature as x, right? So then you can write y as theta 1 x plus theta naught, right? So what I'm going to do, I'm going to introduce one more feature in my x matrix. So let's say this last feature is going to be 1, right? So this n becomes n plus 1 dimensions, right? And this theta is also going to have dimensions as n plus 1 cross 1, right? So this is a vector of n plus 1 dimensions, and clearly the parameters are going to be theta naught up to theta n, right? So we want to find out what are the best set of parameters theta, and one algorithm that we talked about was gradient descent, right, which is an iterative approach. So we say that we have a loss function like this, j theta, and at every step we take some smaller step in the direction of decreasing gradient unless the gradient becomes 0. So at some optimal value of theta the gradient becomes 0, and we say we have find the solution, right? But we can show that this optimal value of theta is given by this equation, right? So I'm calling it as theta star. And now let us talk about how this equation can be derived, or how this result can be derived, right? So I'm going to talk about proof, right? Proof of closed form solution of regression, right? And the loss I'm going to assume here is going to be the squared error loss, right? So loss function can be written as, right, half of sum over all examples 1 to m y predicted minus y actual whole square, right? And where y predicted is going to be nothing but h theta of x, and for a given theta this is going to be summation of theta I xi, right? So this is going to be your y predicted, and I goes from 0 to n. You have n number of features for a given example j, right? So let's say for a given j, right? Okay, so this is your going to be your loss. So y predicted of I minus y of I, right? So what we are going to do, we are going to define few things. Let us first define our input matrix, which is a design matrix. So this represents the ith example, right? And it is a matrix of size m cross n, right? Let us also define capital Y as a vector which contains the labels for all the y values, right? So this is x1 up to xm, right? And let us define y as y1, y2 up to ym. So this is your ground truth, the actual values given in the training set. So it is a m cross 1 dimensional matrix, right? Then let us also define theta. So your theta is going to be theta naught, theta 1 up to theta m, right? This is what your theta is going to be, sorry, up to theta n, right? So it is going to be of size n cross 1, right? Or let's say, yeah, n plus 1, and this is also n plus 1, right? So I'm saying that this matrix includes 1, right? So why I'm including 1? Because when you write hypothesis, right? So if you write h theta of x, this becomes theta naught plus theta 1 x1 plus theta 2 x2 up to so on, right? So I am introducing 1 x naught, which is always 1, right? So we say that if we want to write this equation in the form of theta transpose x, then we should have a x naught which is always equal to 1, right? So in every example I'm going to introduce 1 x naught which is always 1, so that will increase the size of my matrix by 1. So it is going to be m cross n plus 1, and this is also going to be n plus 1 cross 1, right? This is going to be my matrix size, right? And this is going to remain as it is, right? So what we are done is we just introduced 1 x naught for simplifying our formula, right? And this is also written as theta I xi summation over all I goes from 0 to m, right? Okay, so this is about the notation, and from here I'm going to start with the proof, right? So let us first write the loss function, right? So loss function can be written as x theta minus y and square of this term, right? So this loss function is same as writing this. I goes from 1 to m, and here you write y predicted I minus yi square, right? So these two are equivalent. Why? This is called a matrix notation of the loss, right? So this is the loss in the form of matrix notation, right? So let us see what is x theta. So for our simplicity, let us say we have m equals to m, right? And let's say number of features we have is only 2, right? So your design matrix is going to look something like this: x1 0, x1 1, x1, yeah, right, x1 of 2, right? So we have 2 features, and this feature is going to have a value of 1, right? So x2 0, x2 1, x2 2, and up to, right? We have m such examples, right? So xm0, xm1, and xm2, right? So let us see what is this term x theta, right? So I'm defining x and theta. So theta is going to be theta 0, theta 1 up to theta m, right? So what is the product of these two terms, right? So if x naught is always 1, so we are writing 1 here, right? So this is going to be 1 1 1 up to 1, right? So if you see this product, this is going to be this row into this column, right? And we have only m number of features, right? So this is going to be up to x of 2, right? Because we have only 2 features, right? So clearly you can see this is going to give you something like this, theta naught plus theta 1 x1 1 plus theta 2 x1 2, right? Which is equal to theta naught plus theta 1 x 2 1 plus theta 2 x 2 2, right? And so on it go. So clearly you can see this is nothing but the predicted values, right? So this is going to be y predicted of 1, y predicted of 2 up to y predicted of m, right? So effectively what you are getting from x theta is a matrix of y predicted, and if you subtract x theta, which is nothing but y predicted, minus the original matrix, which is y actual, and if you square this thing up, you will get the loss, right? So let me also show you how you can this is going to be a vector, right? So this is going to be a vector of m cross 1, minus this is also going to be a vector of m cross 1, and if you take a square, you are going to get a scalar, right? Why? Because square of a vector is a scalar, right? If you have a vector like this, let's say 1 2 3, and if you want to do the squaring, then this is written as x square is written as x transpose into x, right? So this is going to be 1 2 3 into 1 2 3, right? So this is going to be 1 square plus 2 square plus 3 square, which is equal to, which is a scalar, right? So this is how you're going to get a scalar loss, by writing the same thing in a matrix notation, right? So we can express our loss function as, so j theta, the loss function can be written as x theta minus y and square of this thing, and using the properties, right? So this whole is going to be a vector, let's say this is z, so z square can be written as z transpose into z. So I can write this as x theta minus y transpose into x theta minus y, right? So this is now the loss in your matrix notation, right? So same loss function in matrix notation, right? Earlier you were iterating over entire examples, but now you are just the iteration will be done automatically when you expand this matrix, right? So let us try to open this transpose. So I'm using this property AB whole transpose is going to be B transpose A transpose. Using this property, I can write this equation as, I'm going to take transpose inside, so this will become theta transpose x transpose minus y transpose, and this thing is going to remain same, x theta minus y, right? Now let us multiply all the terms. So this term with this term, you are going to get theta transpose x transpose into x and theta, right? And minus, you are going to multiply this term with this term, which is going to be minus theta transpose x transpose into y, and you are going to multiply this term with this term, so it is going to be minus y transpose x theta plus y transpose into y, right? So this is again your j theta, and now let us talk about how to minimize this loss, right? How to minimize this loss. So we can minimize this loss if the derivative, so this loss again is a convex function as we discussed, right? So this is your j theta. So the loss is minimum at a point where the derivative of j theta, the slope of this line, becomes equal to 0, right? So we need to compute derivative. So let us compute the first derivative, which is going to be delta theta of j theta, right? So we are going to compute this value. So let us write delta theta of j theta, which is going to be equal to delta theta of this equation, right? So theta transpose x theta minus theta transpose x transpose y minus y transpose x theta plus y transpose into y, right? So let us take delta inside. So clearly you can see delta theta of y transpose y is going to be 0 because this term is not dependent upon y. So we are left with only these three terms, right? So here I'm going to introduce few rules of matrix calculus, which you can see on Wikipedia, right? So let me directly define these rules of matrix calculus. How to take derivatives of matrices. The first rule says that if you have a matrix, if you have a vector A, then delta theta of A transpose theta is going to be A, right? Where A is a vector in n dimensions, right? Second rule says delta theta of theta transpose A is also going to be A, where A is a vector in n dimensions. And the third rule says delta theta of theta transpose A theta is going to be 2A theta, where A is a symmetric matrix, right? A is a symmetric matrix, and let's say it is a n cross n matrix, right? If it is not, then it is given as A transpose plus A into theta, if it is not, right? But if it is a symmetric matrix, then A transpose and A are same, and you get this result as 2A theta, right? So using these rules, I'm going to do the differentiation of these matrices and vectors, right? So let us first see this term, right? So this is very similar to this term where A is nothing but x transpose x. So the derivative of this term is going to become 2 into x transpose x, and theta is same, right? And then what you are going to do, you have this term, right? And this term, right? So let us analyze the dimensions of y transpose x theta, right? So y transpose x theta. So y is a matrix of m cross 1. So y transpose is going to be nothing but 1 cross m. X is a matrix of m cross n, and theta is a matrix of n cross 1, right? So the overall result of this multiplication is going to be 1 cross 1, which means it is a scalar, right? And if you have a scalar number like this 5, and if you take a transpose of this, it is going to be 5, right? So transpose, using the property, the transpose of a scalar is going to be a scalar. I'm going to take a transpose of this also, right? So this transpose is going to be, let us see what is the transpose of this number, right? Because it is a scalar, so we can take a transpose, and this is going to be theta transpose into x transpose into y, right? So clearly you can see that this term and this term are now same, right? So instead of writing this term as y transpose x theta, I'm going to say these two terms are now same. So this becomes minus delta theta derivative of theta transpose x transpose y plus theta transpose x transpose y, right? So again, let's see what is this. This is 2x transpose x theta minus, these two terms are same, delta theta of 2 into theta transpose x transpose y, right? And now using this formula, right, because we have a vector theta here, right? Sorry, we have a vector x transpose y here, and we have a theta transpose in the beginning. This derivative is going to be a, which means this derivative is going to be x transpose y. So after taking the derivative of this term, it becomes 2x transpose x theta minus x transpose y into 2, and this should be equal to 0, right? So which basically means x transpose x theta should be equal to x transpose y, and if you multiply both sides by x transpose x inverse into x transpose x theta, this becomes x transpose x inverse into x transpose y. So this term becomes 1, and you get the value of theta as x transpose x inverse minus 1 x transpose y, right? So this is your end result, and this is called your closed form solution of uh, for regression, right? So this is the closed form solution, right? So this is how we can derive the closed form solution for regression, and you can also define this for other algorithms as well, right? So one thing which I want to talk about is when you it would be useful to use this kind of an equation, right? So let us make a comparison between gradient descent and the closed form solution, right? Okay, so the gradient descent is a iterative approach, right? So it is an iterative approach, and you need to figure out what is the learning rate, right? It is a hyperparameter, right? And it can become slow if n is very small, right? And it is particularly useful if you have a bigger data set, right? So what is, and closed form solution is useful, right, if you have a small data set, right, and you get the solution in just one step, right? You directly get the solution, right? But the cost is involved, right? The cost is involved at this point when you have to compute this term x transpose into x, right? So this is going to be a matrix. So x was having dimension m cross n, right? And x transpose x, right? So this is going to be a n cross n matrix, and if data set is a huge, then this inverse could be expensive, right? So it is quite expensive when the data set is large, right? And it is also possible that your data set might not fit into the memory. Then gradient descent is a better approach because you can use a mini batch here, right? The good thing about closed form solution is you do not need to worry about what is learning rate or what should be the optimal step size, and you do not need to iterate, right? But sometimes if the data set is large, it can become expensive, right? So most of the time we use gradient descent because it is quite fast if you have a good learning rate, and generally data sets are large, and doing stochastic or mini batch helps a lot, right? So this is about the closed form solution, right? So we started from a loss function. We saw how to minimize the loss function. So loss function is having a minimum when this derivative becomes 0, right? So we need to make this thing as 0, and we find out that value of theta which minimizes the loss, right? So I hope this entire mathematics of closed form solution is clear to you, and if you like the video, do press the like button and subscribe our channel. Thanks for watching.